Oh, nice. Well, Joseph. All right, good afternoon, everybody. Jim Jackson, the director of Green Bank Observatory. Welcome to this week's community Zoom. We have actually have a guest from Belgium today, so very good. Thanks for joining. I begin these weekly events with a bit of an update on the status of the observatory. Had some bad weather the last week that has forced a little bit of a snag in our operation schedule, but we're back on track. The call for proposals is out, so you should be busy writing your Green Bank proposals. The due date is February 1st. We sent out our letters of disposition for the special call last week, and we approved several new proposals for large projects using low frequency receivers. There is a special event coming up on February 2nd. So because the AAS was canceled, we're going to have a special session where we were going to give the talks that we normally would have given at the AAS. So check your emails and our website for details. We're looking at the schedule now, but it will start February 2nd at about 2 p.m. and we'll go for an hour or two, depending on the number of talks. So that's the news from Green Bank. Let me pass it over to Dave Freyer, who will introduce this week's speaker. Take it away, Dave.
Hi, my name's Dave Freyer. It's my pleasure to introduce our speaker today. It's our own recently hired postdoc at our observatory, and we're happy to have her here today, Emily Moravec, and she'll be talking about exploring merger galaxy clusters and radio galaxies at Z of order approximately redshift at 1. If you guys have questions, please put them in the Q&A, and we will take care of the questions at the end of her talk. So Emily, go ahead and take it away. Thank you.
Thanks for the introduction, Dave. So hi, everyone. My name is Emily Moravec, and I want to thank GBO for giving me the opportunity to talk about my work today. So today I'm going to be speaking about the work I have done investigating the interplay between radio galaxies and galaxy clusters, specifically merging galaxy clusters at a high redshift, redshift of about 1. But first I wanted to speak a bit about galaxy clusters and radio galaxies to give you some context. So galaxy clusters are the largest gravitationally bound objects in the universe, and they have 3 different identifiable components. They have dark matter, which consists of 80 to 90% of the total mass of galaxy clusters. And then there is the superheated plasma that is called the intercluster medium. It is a hot gas that has a temperature of about 10 to the 7 or 10 to the 8 Kelvin. And it makes 10 to 15% of the total mass of galaxy clusters. And you can see this here in this image in the purple. And then there are finally the galaxies in the galaxy cluster, and they make only a few % of the total mass of galaxy clusters. So there are a lot of different types of galaxies that can be in a galaxy cluster. And one population is the radioactive galactic nuclei, or radio AGN. And an AGN is a type of galaxy that has substantial amounts of radiation beyond what can be explained beyond typical processes such as star formation, is confined to the center of the galaxy. And it has 3 identifiable components as well. You have the black hole, and then the accretion disk, which then has matter that is falling onto the supermassive black hole. And then you have the jets, which extend radially outward, and they emit synchrotron radiation, which can be seen in radio wavelengths. So radio AGN, or AGN, that have these identifiable radio jets. There's a lot of interesting physics that can happen with these jets. Specifically, it has long been known that there's a coevolution between radio AGN and galaxy clusters in that they affect one another. So on one hand, you have the galaxy cluster environment that can affect the size, the shape, and the luminosity of radio galaxies and radio AGN. And on the other hand, radio AGN can impart significant amounts of mechanical and thermal energy into the intercluster medium and into the galaxy cluster. And so you have this interplay between the two. And what is interesting is that this relationship evolves as a function of redshift. So it has been found that galaxy clusters at higher redshift have more radio emission, specifically coming from radio AGN at higher redshift. So at this epoch of redshift of about 1 is this golden opportunity to investigate this interplay between radio AGN and galaxy clusters to see how the two affect one another. Enter in the massive and distant clusters of WISE Surveyor MADCOWS, which is a catalog of about 2,700 galaxy clusters at this important epoch of redshift of about 1. And we created this catalog by cross-matching infrared and optical data, applying color and magnitude cuts to isolate galaxies at this redshift, and then applying a smoothing kernel and extracting overdensities to get this really interesting sample of galaxy clusters. So with this large sample, we can conduct a lot of interesting investigations into galaxy and cluster evolution at this epoch. So I spent a few years investigating this relationship of radio AGN in their environment with radioactive cows. And I did this by identifying the MADCOWS clusters that had the most extended radio sources, and then following them up with a VLA observing campaign over 3 semesters to characterize the radio AGN in these galaxy clusters. So that's how you get a radioactive cow. You have radio observations of active galaxies in MADCOWS clusters. So here are some eye candy, some of the images that I made from the data. And you have a lot of different types of radio galaxies here. It's not particularly important for the work I'm talking about today, but you have the Faranoff and Riley, or FR, classes 1 and 2. You have hybrids. You also have these bent tail radio galaxies where you have the jets become bent due to the interplay between the intercluster medium and the radio galaxies. We also have infrared data for most of the MADCOWS clusters, which allows us to identify the host galaxies and investigate their properties. So those are the background images here with the radio contours overlaid. And you can then calculate the stellar mass of the host galaxies of these radio galaxies. And I found that 40% of the host galaxies were the brightest cluster galaxies, so the most massive galaxies in the galaxy cluster. And 83% of the host galaxies were in the top 6 most massive galaxies in the cluster. So I found that the radio galaxies, their hosts, were amongst the most massive in the galaxy cluster, which is interesting. So as I mentioned in the introduction, it's interesting to investigate this interplay between properties of the environment or the galaxy cluster and properties of the radio galaxies and the radio AGN. So I looked at a lot of different correlations between various properties of these two objects, the galaxy clusters and the radio galaxies. I didn't find correlations between these properties, between the luminosity of the sources of the radio galaxies and the distance from the cluster center, or with richness, which is the number of galaxies in the cluster. But I did find some evidence of other correlations, such as it's interesting that 48% of the radio galaxies are the brightest cluster galaxy. I also found a relationship between the size of the radio source and the distance from the cluster center. And I found that the most compact sources are the most massive and they're near the cluster center. So all of these things together mean that I found that the cluster environment fosters radioactivity, especially for those massive galaxies near the cluster center, but it's not the sole driver of the evolution of the rest of the population. So this work sets the background for the work that I am conducting now and the work that I use the GBT data in. So while I was investigating radioactive cows, I found this really interesting cluster, MOVE 1506, and it stood out amongst the rest of the radioactive cows in a couple different ways. It was one of the 50 clusters, the only one that had 5 radio sources near the cluster center. And it was one of only 2 that had extended radio AGN near the cluster center. And it was the only one out of all of the 50 clusters that had bent tail radio sources. And thanks to the multi-wavelength data that we have, we can look into why is this cluster different from the others. It could be the small scale activity or large scale activity. But through 3 lines of evidence, I found that this is emerging galaxy cluster. It's an emerging system. And so I looked at the spatial distribution of the galaxies, and there was a lot of substructure indicating that it's an emerging environment. And then through the radiomorphology of the jets, I don't have time to go into that, but that was indicative also of emerging system. And lastly, I used the GBT data to calculate the mass of the cluster, and comparing it to other galaxy clusters, found that it was emerging system. So this is interesting. So it seems to be indicative that what's different about this system is that it's merging. So quickly about the GBT data. So we can use Mustang II on the GBT to observe the Sunyaev-Zildovich effect, which is the effect where you have CMB photons interacting with the hot gas, the intercluster medium, and then these CMB photons gain energy and then are blue shifted. And then you see a decrement of photons at specific frequencies. And that decrement is then proportional to the mass of the galaxy cluster, which is what you see here. You can see that decrement of photons. And so here is the pretty picture. So this is VLA data to show you the structure of the AGN jets. And then the GBT shows you the intercluster medium in this cluster. So as I mentioned, we can use that decrement to then identify and calculate the mass of the galaxy cluster. And for mad cows clusters, we found this mass richness relation, that there's this relationship between the mass of the galaxy cluster and the number of galaxies in the cluster. And you'll notice that there are a few off to the right and that are identified in red. So these were identified to be merging galaxy clusters, and they were identified with Chandra data to be such. And Simon Dicker kindly calculated the mass of MOVE 1506, and it lay with these other merging systems. So that's how the GBT was crucial to this study to learn about this interesting cluster. So why would the merging clusters lay in this area of the diagram? Well, as you have 2 merging systems, you'll notice that in the yellow circle, the number of galaxies, the white points, increase inside this circle before the 2 systems have a time to coalesce and have the intercluster medium, or the orange, coalesce and form, and then boost the SZ signal that we get. So that makes sense why those systems are over to the right then, because you see an increase in these merging systems in the number of galaxies before the ICM has a chance to coalesce and increase the SZ signal. So we had these 3 lines of evidence of why the MOVE 1506 is a merging system. So our interpretation then is that it's the dynamical state of this cluster that is affecting the radioactivity and causing this high amount of AGN activity. So now I'm asking the question, is enhanced radio AGN activity ubiquitous in merging systems, or is MOVE 1506 just different for some reason? So I am currently working on a sample I've collected of about 200 merging galaxy clusters across a full redshift range. And I'm doing several different studies, but using survey data to compare these merging clusters to non-merging systems, to look at the spatial distribution of radio galaxies in these systems, to look at their morphology, to see, do merging clusters really enhance radio AGN activity. And so I have a VLI program that just was completed to compare merging and relaxed clusters at high redshift. And then I also have an SMA program that's currently being completed. Hopefully that I'll be able to analyze the molecular gas content of the host galaxies and to learn more about the SEDs of the radio AGN. And then proposing with the GBT to look at some particular merging systems to really probe the ICM structure and understand the interplay between the ICM and radio AGN. So in the last little bit of my talk here, I wanted to talk a bit about the work that our Mad Cows team has done with Mustang II. So over 5 semesters, we've observed 27 galaxy clusters to observe the SZ effect. And you can see on the left here an example of the SZ decrement that we have in a very massive cluster. And then on the right, you can see the SZ contours overlaid on top of a galaxy density distribution. And for the first 16 clusters, Simon Dicker has published a paper to expand on that mass richness relationship that I was showing before. So earlier where that gray is, that was the original mass richness relation that we found. And then after we've added all these clusters, this relationship has increased in scatter, and it may even have another branch to it. So we're currently looking into this more, which is really quite interesting. So overall, I talked about the work that I've done with radioactive cows of investigating this interplay between radio AGN and galaxy clusters. And I found that the cluster environment fosters radioactivity, especially for those massive galaxy clusters or galaxies near the cluster center. And then I've done some interesting work with this particularly interesting cluster, Mu-1506, that had higher radioactivity than the other radioactive cows. And it seems that during the galaxy cluster merger phase, radioactivity can be dramatically enhanced. And I currently have several observing campaigns to look into this. Is Mu-1506 on its own, or is high radioactivity ubiquitous in merging galaxy clusters? And if it is, what's the common denominator? And if not, why is Mu-1506 different than all the others? So thank you for your time, and I will stop for questions.
Thank you very much, Emily. So those with questions, go ahead and put them in the Q&A box, if you would, please, and we'll take them. While we're waiting for questions to come in, I'll just jump in and take my, the picture of the 1506 with the GBT data. Could you bring that up? I was just curious, where's the noise level at that? Is that the blue in the background?
Yes. So the GBT is the
blue.
And so it is, what I did is I overlaid, this is the signal to noise of the SZ effect. And so this is, so it's signal to noise. So the noise has been, so everything you see is signal.
Okay.
Yeah, that's a good question.
Signal meaning above, is there a thresholding? Because I can see a darker blue. I see structures that look, well, I was just wondering what's significant, how far away, how much of that blue?
Yeah, that's a good question. So this was more for a beautiful image sort of thing. So I think this was about, I think it was 8 to 10 signal to noise.
Oh, okay.
So
high
black,
signal. Okay.
Yeah. So it's like 8 to 10. And then I would say as you get, so any black was actually positive. So it's actually negative signal because it's SC.
Okay, so you inverted it. That was going to be my other question.
Correct.
I wasn't sure how.
Yes, so I inverted it to really show off the the GBT data. So yeah.
Okay, so the brighter blue, it shows the deepest decrements.
Right, exactly. Yes.
Okay, thanks for that
Yeah,
clarification.
thanks for the question. Yeah.
Okay, we have a question that just came in. Why and how mergers enhance member galaxies activity? It seems, and so it's a question on why and how do you think mergers enhance members galaxies activity? It seems merger process will not significantly increase the relative velocity between the galaxies and the ISM.
Yeah, it's a good question. I think what they're asking is, what is the physical mechanisms that would actually enhance this radioactivity? So it's a good question, something I'm currently looking into. But some ideas are that, yeah, it wouldn't necessarily increase the relative velocity, but it will increase the number of interactions that could occur between galaxies. So then this could perturb the accretion disk and cause matter to flow down to the AGN engine and create fuel. Another possibility is that shock fronts. So when you have a merging system, you will be generating shock fronts, and then this could then affect the individual galaxies and cause, again, this could push fuel down to the AGN engine. And that's actually what I would like to use the GBT to investigate further, is to investigate that particular mechanism, if shocks correlate with the placement of the radio AGN. So thanks for the question.
Another question, are there other unifying features of radio sources that are not in the top 6 most massive galaxies in their cluster?
Oh, no, that's an interesting question. So I didn't see any. Mostly, it's the fact that the most massive galaxies emitted radio emission at all. I didn't see any radio emission from the less massive galaxies in the cluster. So yeah, that's an interesting question. So of the sources themselves, not as much. And I didn't look into that, but it could be interesting actually to look further into that.
Okay. I'm going to jump in with just a question. I do a little bit of high redshift, and I've always been fascinated with the fact that sources or systems that show enhanced AGN activity also have enhanced star formation activity. I was wondering, on these clusters, have you looked at the star formation properties and these things to show, have you looked at that angle yet?
Yeah, that's a really good idea and point. I actually have seen some papers that have looked at that. Looked at the star formation activity, and they do see some enhancement. I would like to do that. So with the VLA data, I'm hoping that I might be able to do that.
Go deep enough?
Yeah, it was just on the cusp
okay.
to have gone deep enough. I was mainly going after the radio AGN, but I might be able to catch some. So that's a good point and a good idea. So some people have seen that, and I would like to go ahead and look into that further.
Okay, we have another question. They put a caveat, perhaps a naive question from a non-galaxy person. Okay, on long time scales, would the merging clusters on the mass number plot move to the left as they merge, move up as the cluster medium becomes denser, or none of the above?
Yeah, that's a great question. And my understanding is that they would move up. So they would stay with the same number of galaxies in the cluster, but as they coalesce and the ICM of the substructures coalesces, that will increase the SZ signal. And so that increases the SZ mass. And so they would move up to that plot, in that plot, to then lie on the relation. That is the ideal case. But as you saw with the rest of the Mustang II data with the mad cows clusters, it's a muddied picture, but in general, physically, that is what should happen, that they move up as they coalesce. So yeah, interesting question.
Okay. Sure. Okay, we have no more open questions right now. I'll give a little bit of time and just blabber opportunity to add more questions. The slides were quite visually I mean, you did a nice job on your slides.
you.
I was impressed by that. I have never seen that outline style where you could follow along your outline based on, well, anyway, how you did the slide border as well as the pictures on there. So that was a very good job on your talk today.
Thank you.
And it looks like we don't have any more questions coming in.
Okay.
So Jim's video just came on to you. Jim.
I just want to make a comment. Mad cows and radioactive cows are one of the best acronyms I've ever heard. So that's
Thank
astonishing.
you. Yes, I thoroughly enjoy that.
Better than hot dogs or the dusty. Never mind. We did hot dogs or dusty dogs. But anyway, I agree. Okay, well, thank you everybody for joining our seminar today. And I think we do these every 2 weeks, and I did not do my due diligence to see who's up to bat next. So I apologize. Hopefully another great talk. So join us again in a couple of weeks. So thanks, Emily.
I can chime in on that there, David.
Hey, Paul.
February 2nd, we have Eric Cox from CFA doing a detailed atomic ISM kinematics across the local group with the GBT and the VLA.
Thank you, Paul, I should have done my background work.
No worries. I got the webpage
Okay.
open. So.
Okay. Well, thank you, everybody. Bye.
Thanks. Bye.